Hi, welcome back. Today we will be talking about polar equations of a conic in Pre-Calculus 2 honors. So to start with, let's go ahead and recap something from for not last semester, but maybe like say about I don't know, maybe about 2 months ago. It's something called eccentricity for conics. And the way we defined it back then was that it's supposed to be a ratio of c over a, where c is supposed to be the distance from the center to the focal point, and also a is going to be the major radius or the transversal radius. So basically from the center to the outer part of the conic. And yeah, so that's going to be eccentricity from how we defined it back then. Now, there was something else that goes along with it. If E is equal to a certain value, because it's supposed to be a ratio, then that tells you what kind of conic it is. So the four different types of conics that we have is the circle, ellipse, parabola, and hyperbola. So when we first encountered the eccentricity, we saw it in the ellipse because we said that the distance from the center to the focal point is always going to be less than the major axes or the major radius in this case. So E for the ellipse is supposed to be between the ratio of 0 and 1. But whereas if you have E is equal to 0, meaning that the focal point becomes closer and closer to the center, then that becomes a circle. And then after that, we have the hyperbola because the focal point is always going to be outside of or it's always going to be a longer length than the distance from the center to any point that is on the hyperbola. So hyperbola E is going to be greater than 1, and the last one will be when E is equal to 1 because of, I guess, pigeonholing everything. So that is where we're going to have E is equal to 1 for the hyperbola. Now, there is actually a better or more formal definition than this because what happens is that the author defined it as C over A just for simplicity. The more formal definition that you're going to run into is the following. E, which is still a ratio, but this time it's a ratio where the numerator is supposed to be the distance from any point from the conic to the focal point, and then divided by the denominator, which is supposed to be the distance from that same point to the directrix. And believe it or not, every single conic does actually have a directrix. It's not just the ellipse, it's not just the parabola, and it's also going to be for the circle and the hyperbola, which we technically don't really see too often, or we don't really care too often, but it's actually there. So here's kind of like a picture of what's happening, and there is an illustration as to what is actually what we're doing in all of this. So here you can see the focal point is inside the conic, and P is going to be any point that's on the conic, and the directrix is always going to be on the opposite side, where the conic is kind of like right in the middle of between the two. So we're going to look at that ratio, and again, depending on what that value of E is equal to, we still have one of the four conics then. So what I'm saying is that all of these right here, where if E is equal to 0, then it's a circle. If E is between 0 and 1, it's still an ellipse. If E is equal to 1, we still have a parabola. And if E is going to be greater than 1, then we have a hyperbola. That part we still hold. It's just that now we're using a more formal definition, so then that way you can utilize this equation a lot better, or eccentricity a lot better. So let's go ahead and derive this equation so you can see how that actually looks like in polar form. So there is one really big restriction that we have to go by, and that's the following. Let the pole be the focal point, or let the pole be a focal point. If your pole is not a focal point, we actually can't do this at all, which is very restricting. Yes, I know, but it's actually not too bad because all we have to do is if we want another equation, we just basically translate it. But for right now, that's going to be our big assumption right there, okay? So you can see on the graph, you now have the pole, which is denoted as point O. P is going to be a point on the conic. And remember, this conic right here, that's just a general shape. It's not necessarily a parabola. It could be an ellipse. It could be a hyperbola or whatever it is. Then you have the directrix, which is on the opposite side. So we're going to go ahead and look at E, the eccentricity, as that ratio then. So E is equal to the numerator, again, which is supposed to be the distance from any point on the conic to the focal point. So in our picture right here, that's going to be PO. Then divided by PM, which represent then the distance from that same point to the directrix. Now, let's go ahead and write something in there so then that way you can see how we can derive the equation. So first off, I am going to maybe draw the picture on the side so you can actually kind of see a little better. Actually, Mo, maybe I can probably use what's inside over here. Hopefully you guys can see. So first start with PO, okay, PO. Because this is in polar coordinate, then that means that the length of PO right there, that's really just R. Remember, this is in polar form, right? So that's just the radius, which represents the distance from the origin to that point. So we can go ahead and replace it, PO with R. Then that's going to be divided by PM. Now PM, that's going to consist of two parts. And let me go ahead and kind of like erase this part so you can kind of see it a little bit better. So let me erase that and then erase this guy and erase this guy. And if I kind of like draw PM on the bottom over here, right? So there's going to be P and then that's going to be M over here. You'll notice that PM really consists of two parts. Here, where I break it, that is really going to be kind of like the y-axis. So what that means is you have one segment over here, and then you have another segment over here that makes up PM. Now, first, we're going to look at this piece over here. And that piece is a piece of a right triangle, right? The right triangle where, oops, sorry, skip that a little bit, come back over here. That is going to be a side of a right triangle where the right triangle has the following right here. Here, again, remember it's the origin. Here is supposed to be R from what we had earlier. And remember that this angle is supposed to be theta. So if you look at it carefully, using a right triangle, then that means that that length right there, that little small little sliver, is supposed to be R cosine theta, okay? Because this guy right here, that is supposed to be, like we said in the picture, R cosine theta because it's supposed to be the horizontal side. Now, as for the other piece over here, well, we don't know what that is, so we'll just go ahead and give it some value, I guess. So we'll go ahead and call it D, I guess. So for the time being, let's just go ahead and say D. So then that means that PM is going to be some distance D, which is going to be the distance from the origin to the directrix, plus R cosine theta. So there is our general equation of a conic. And what I need to do is solve for what R is equal to because I need to get it into a form that we can actually utilize. So let me go ahead and clean it up a little bit. We're going to cross multiply first, or we're going to multiply to both sides of the denominator. So we have E times D plus E times R times cosine of theta is equal to R. Focus here, I want to solve for what R is equal to, okay? So E times D is equal to R, and then we have minus ER cosine of theta. Then we're going to factor out the R, so R multiplied by, in parentheses, 1 minus E cosine theta. And then we have ED on the outside. And finally, when we solve for R, right, that is going to be equal to E times D divided by 1 minus cosine of theta, and then multiply by E, which I missed out over there. So let me go ahead and replace it back in. So we have 1 minus E cosine theta. So there we go. That is going to be our general equation of the conic then, okay? Again, keep in mind, the E is supposed to be the eccentricity, and then the D is supposed to be the distance from the y-axis to the directrix, which in this case, we don't really care too much about, and you'll see why in just a little bit. Okay, so as soon as we have this form right here, then that means that we can recognize it as a conic and we can work with it. So let me go ahead and go into an example to show you what I mean by that. So here you can see that we have a typical equation that falls into that category of the conic then. So we have R is equal to 12 divided by 6 minus 4 cosine theta. So the very first thing is we need to identify what kind of conic it is. Looking at our general equation that we're working with, you'll notice that the one part that is going to stick out is that you have a 1 over here. And so what that means is with our equation, I would like to make that 6 into a 1. So we'll go ahead and first divide both top and bottom by 6. So then that way we can get that 1 right there. And that would then give us R is equal to 2 divided by 1 minus 4 divided by 6 cosine of theta. And right there, that 4 over 6 right there, that's going to tell you what type of conic it is. Because 4 over 6, which is the same thing as 2/3, is a number that is between 0 and 1. That tells me that this is going to be equal to a ellipse, okay, an ellipse then. So that is my identification. And as soon as you know that's an ellipse, then now we can go ahead and sketch it out then. Keep in mind, once again, that the pole is going to be the focal point. So we're going to go ahead and make sure that's going to be the case. So just like what we've been doing so far, and we haven't changed anything yet, we're going to go ahead and find a few points that's going to be on this ellipse. So there's 0, so there's theta, and then there's r. So for the values of theta, we'll keep it consistent. We'll still use 0, we'll still use 90, 180, 270, and then finally 360. So plug it into the equation, let's see what we get. So first off, if we plug in 0 into the equation, we get 12 divided by, in parentheses, 6 minus 4. So that looks like it's going to give us 12 divided by 2, which is equal to 6. At 90, you're going to get 12 divided by 6 minus 0. So that answer is going to be equal to 2. At 180, you get 12 divided by 6 plus 4. So that gives me 12 divided by 10, which is equal to 6 over 5. Or if you want, you can say 1.2. At 270, you get 6 minus 0 once again, so that gives you 2. And finally, 360, that's going to give you 12 divided by 6 plus 4. I'm sorry, 6 minus 4. So that will give you 6 once again, just like before. So let's go ahead and plot those points. So the first one is going to be radius of 6 and a and a degree of 0. So that is going to be somewhere over here. Next, at 90, you have 2. So that's somewhere over here. Oh, sorry, a little bit too high. So let me go ahead and change that right there. So that's going to be this. At 180, you get 1.2. So that's like somewhere over here. And then finally 270, which is going to be 2. That's going to be over here. And again, looking at the 4 points, you can definitely see the ellipse that we're supposed to be graphing. Now, keep in mind, if it helps you, again, that pole, the origin, remember, that is supposed to be a focal point. And so with all those 5 points, you can definitely now see the ellipse then. So we're going to go ahead and sketch that out, and that's going to be it. So it's going to be something like this then. Okay, you don't need to find the other focal point. You just have to sketch out what this graph actually looks like, and then we're done. So that's it. That's basically the goal of each one of these. Take your equation of r and then the equation of the conic. First, find out what is the eccentricity. And then afterward, once you establish the eccentricity, what type of conic it is, then you find 4 points. And afterwards, sketch the graph of it. Okay. So let's go ahead and do 2 more examples, and then that should probably do it. So here we have r is equal to 14 divided by 2 minus 2 sine theta. Now, once again, I'm going to go ahead and divide both top and bottom by 2 because I have a 2 right here, which I want to change into a 1. So r is equal to 7 divided by 1 minus sine of theta. And that technically gives me like a placeholder of 1 that's next to the sine. Now, if you're wondering, does the trig function really matter? The answer is no, right? Because if so long as you have a trig function there, cosine or sine, then that means it's going to be the conic. And in terms of what's the difference between one versus the other, it's just the orientation of the conic then. So it's either, like rotated to the x-axis. Oh, I'm sorry. It's going to be like bigger in the y-axis or bigger in the x-axis and so forth, that kind of stuff. Nonetheless, going with what we have right here, since the eccentricity is equal to 1, then that tells me that this is going to be a parabola. Okay. Now let's go ahead and see how that comes out to be a parabola. So let's have the angle theta. We have the value of r. We're going to also use 0, and then 90, 180, 270, and then finally 360. I'm going to give myself a little bit more space because I didn't do it on the last one. So here we go. Let's go ahead and plug in. Let's go ahead and plug into either one of those equations should be okay. So plug in 0 at the very beginning. You're going to get 14 divided by, looks like it's, let's see, 2 minus 0, so that's equal to 7. Then at 90 degrees, you have 14 divided by, looks like we have a little small problem, 2 minus 2, which is going to be undefined. Now, technically, like 14 over 0, that's kind of like saying that it's going towards infinity. So we're just going to keep that in mind for the time being. Next, we have 14 divided by, again, 2 minus 0. So that would give us 7 once again. Then we also have 270, which is going to be 14. 14. Let's go ahead and clean that up a little bit. 14 divided by 2 plus 2. So that would give us 14 over 4, which is equal to 7 over 2. So it's like approximately 3.5. And finally, at 360, we get the same thing as before, which is 14 over 2. So the answer is equal to 7. So you'll notice that probably it's going to be kind of weird because we only have 3 points to work with. But it's okay because remember, this is a parabola. And so we should expect something like that. So let's go ahead and see the graph. 7 radius and the theta value is equal to 0. So that is going to be a point that's over here. 90, and then it's going to open towards infinity. Now we technically can't graph that, so keep in mind we just don't even touch it for the time being. Okay, so so basically it's like kind of saying as you rotate towards 90 degrees, your values of r is going to be really big. At 180, you're supposed to get 7, so that is approximately over here. Then we have 270, which is 3.5, so that is going to be approximately over here. Now 360 comma 7, we go back to the very beginning. And once again, keep in mind the very key thing is the pole is again always going to be the focal point. Now, hopefully you can see what the parabola actually looks like. And now that actually matches up with what we're saying, right? If we draw the parabola as it is, that tells me that, yeah, we're going to be opening upward. And that now makes more sense because remember, when you rotate 90 degrees, your radius is going to get bigger and bigger, which is going towards the upper part. So at 90, so r is going towards infinity. So there is your sketch of the parabola then. Okay, not exactly nicest, but you know that's give or take something. Okay, let's look at the last one over here. So you can expect what's going to happen. If we looked at ellipse already, we looked at parabola already. The last one is probably going to be a hyperbola in this case. Oh, and by the way, thinking about what we've been doing so far, if we did have a circle, it would probably read something like 16 divided by 3 plus 0 times sine of theta is equal to r. And you can see why that's a circle because then the trig function cancels out, leaving you with r is equal to 16 over 3, which tells me that you're just graphing the radius. Okay, so for that reason, that's why we're not doing the circle because it's very trivial. All right, so here's the last problem, and I do recommend that, you know, at this point, if you get the idea as to like how to do these problems, try it on your own, pause the video, and then come back and see if it's going to be correct. If it is, great. If it isn't, well, you have something to refer to. Okay, so here we go. Last one. We're going to divide everything by 3, right? And let's see, what do we get over here? Actually, you know what? I just realized something. Looking at the value that I just gave you, we're probably going to end up with an ellipse because if I divide by 3, it doesn't look like we have an eccentricity that's greater than 1. So let me go ahead and modify the problem right now. And, you know, for me, the best way I can describe what I'm doing is I'm basically building the plane as I am flying it. So that's kind of like my model right now, unfortunately. So let's see, my pen is not working properly. So let me go ahead and write it over here on the bottom. R is equal to 16 divided by, let's say 3 plus 4 cosine of theta instead then. Okay, so let me go ahead and get rid of this guy all over here and it's not showing up. So we're just going to try not to look at it. Okay, here we go. First, again, we're going to go ahead and divide everything by the 3, right? And this problem, the numbers are not going to come out nice, unfortunately, because I just kind of came up with these numbers on the spot. So if we divide by 3, we're going to get r is equal to 16 over 3 divided by 1 now, right? Plus 4 over 3 cosine of theta. So that tells me that e is a number that's greater than 1 because it's equal to 4/3. So therefore, the graph is going to be a hyperbola. Once you establish this type of graph it is, then we're going to go ahead and sketch it out by plotting points. So we'll go ahead and find 4 points to work with, hopefully. Here's theta, here's r, that's 0, 90, 180, 270, and then finally 360. Okay. So at 0, when you plug it in, and remember it's this equation now because I kind of goofed up earlier, we are going to get 16 divided by, looks like it's going to be 7. So it's not exactly a nice number. That's approximately what, 2 and 2/7. Okay. Now we're going to go ahead and plug in 90 degrees, which is going to give us 16 over 3. So whatever that comes out to be, that's like 5 and 1/3. Okay. I will keep going. At 180 degrees, you are going to have 16 divided by 3 minus 4, so that's going to be negative 1, so that's going to be negative 16. So that's a big negative number, so we'll see how to deal with that. 270, we get 16 divided by 3, and so again, that gives us 5 and 1/3. And finally, with 360, that should give us 16 over 7 once again, which is 2 and 2/7. All right, so let's put it all together. So first point, a radius of 2 and 2/7 and the angle of 0. So that is going to be somewhere over here, pretty small for the most part. At 90 degrees, we have 5 and 1/3. So 1, 2, 3, 4, 5. So we're going to go up by that much. And there's the next point. After that, at 180, you get negative 16. Now be careful, negative 16. So that means we're not going in the 180 direction, but we're going to go out into the x direction into theta's, sorry, when theta is equal to 0. It's like kind of like saying radius of 16 comma 0. So this point right here, we really treat it as 16 comma 0 degree. So that's going to be like far out there on the right hand side. Now I can't quite reach over there, but you get the idea. Next, we have 270 and 5 1/3. So we're going to go 1, 2, 3, 4, 5. We'll go down by that much. And there's the point. And lastly, 360 comma 2 and 2/7. So that means the same point. And once again, just for our reference sake, I'm going to go ahead and draw the pool as a purple dot to indicate that it's a focal point. So there, with the 4 points, you should be able to see the hyperbola in this case, hopefully. The hyperbola looks like it's going to be the following. Kind of like the parabola that's opening sideways, opening towards the left-hand side in this case anyways. So that's going to be your first part. And for the other side, now remember, that point right there, that is going to be kind of like the symmetric point to the point which is 0, 2, and 2/7. So that tells me the parabola on the other side is going to be something like this then. Okay, so one is opening one direction towards the left, the other one is opening the other direction towards the right. And it does look like everything is matching up because again, it is horizontal. It's opening towards the left, opening towards the right, which tells me, yeah, that should match because remember, we have a cosine equation, which tells me that it's going to be an x-related type of graph where everything is going to be horizontal. Okay. All right, so that should do it. So thank you again for watching. I will see you guys next time.